Sabrina, for your kind introduction. Ladies and gentlemen, good afternoon. Before starting my presentation, I'd like to thank my co-authors from the Federal University of Pampa in Brazil for their valuable collaboration. The goal of this study is to really investigate the mechanical behavior of nanosilica modified pervious concrete from both experimental and numerical points of view. In particular, my presentation is organized as follows: a brief introduction, the description of the experimental program and of the main results, calibration and validation of the lattice discrete element model, and finally, the conclusions. Nowadays, the use of pervious concrete as a pavement material in low-volume roads represents a best management practice to mitigate the problem of stormwater runoff. Its macroporous structure enables rapid water infiltration, thereby reducing stormwater runoff and promoting groundwater recharge. Moreover, several studies have highlighted additional benefits such as noise reduction, improved thermal performance, and enhanced quality of the urban runoff. The distinctive feature of pervious concrete is its high porosity and high permeability, which are achieved by using coarse aggregate, either single-sized or open-graded, with sizes typically in the range 5 to 19 millimeters, with little or no fine aggregate. Consequently, the void content generally varies between 15 and 35%. However, as it is well known, the presence of pores negatively affects the material strength, and consequently, such a drawback can be mitigated by incorporating nanoparticles such as nanosilica, which, as reported in several studies, improves mechanical properties of cement-based materials through pozzolanic reaction, hydration process, acceleration, and a filling effect. In the present experimental campaign, raw materials include a crushed basaltic stone as coarse aggregate, a natural river sand as a fine aggregate, Brazilian Portland cement, a superplasticizer based on modified polycarboxylic ether polymers, water, and nanosilicon dioxide with particles in the range 15-35 nanometers. The particle size distributions of both aggregates are here plotted, and they have been adjusted in order to achieve a porosity of about 20%. Two mixtures are prepared, a plain pervious concrete named PC in the following, and a modified one containing about 3% of nanosilicon dioxide by cement weight named PCN. The two mixtures share the same matrix composition shown here in the table, with the exception of the superplasticizer content. And such a mixed design has been obtained by using the compressible packing model, aiming to achieve a compressive strength of about 14 megapascal, with a porosity of 20%, and a maximum content of fine aggregates equal to about 20% of the total aggregate. For the PCN, the superplasticizer content has been increased up to 1% in order to obtain a workable mixture with a wet metallic appearance. For specimen preparation, about 10% of water is mixed with aggregates for about 30 seconds. Then the cement is added together with the remaining water with the superplasticizer, being mixed for about 5 minutes. For the PCN, the nanosilicon dioxide is predispersed in about 50% of the water for about 5 minutes before adding to the mixer. The fresh concrete is then casted into types of molds, cubic ones for infiltration and compression tests, prismatic ones for density, porosity, tensile, and bending tests. Finally, the specimens are compacted with a manual roller in order to simulate in situ compaction, aiming to achieve the theoretical density. After 78 hours, they are demolded and cured in a humidity-controlled chamber for 7 days for infiltration test, 21 days for density and porosity tests, and 28 days for mechanical characterization. The infiltration rate is measured on 3 prismatic specimens according to the modified ASTM standard, and the mean value is equal to 0.82 centimeter per second for PC and 0.49 centimeter per second for the PCN. Both values fall within the range recommended by the ACI report, although the PCN exhibits about 40% lower permeability with respect to the PC, probably mainly due to a particle filling effect and the lower workability, which lead to the formation of a denser surface layer. Regarding the hardened density and porosity, they are determined on prismatic specimens, and the average values that are here reported are in agreement with the design ones. The compression strength is determined on 5 cubic specimens loaded in the compaction direction. The mean value is equal to about 13 megapascal for PC and about 11.7 megapascal for PCN. Whereas the splitting tensile strength measured on 6 prismatic specimens loaded again in the compaction direction is equal to 2.64 megapascal for PC and 2.27 megapascal for PCN. Finally, the flexural strength is determined on other 6 prismatic specimens by performing 4-point bending test and by instrumenting the specimens with an LVDT to record mid-span deflection. Also, in this case, the load is applied in the compaction direction. The flexural strength mean value is equal to about 2.42 megapascal for PC and 2.26 megapascal for PCN. The corresponding values of the elastic modulus are about 14 gigapascal and 13 gigapascal, respectively. This lack of improvement in the mechanical properties of the PCN is attributed to the lower workability and higher compaction issues, leading to a significant density gradient. A gradient that has been verified by cutting both PC and PCN specimens into 5 slices in the compaction direction and by measuring the density of each one. It has been observed that for PC the density decreases of about 7% from top to bottom, whereas for the PCN this variation reaches about 20%. Now, moving to the numerical simulation, the lattice discrete element method here employed represents a continuous medium as a 3D array of nodes connected by massless uniaxial elements capable of transmitting only axial loads. The masses are discretized and concentrated at nodes, each characterized by 3 degrees of freedom. And the discretization strategies employed a cubic module consisting of 9 nodes connected by 20 bars with length L and total mass M. To describe the fracture process, a trilinear constitutive law, originally proposed by Kosteski et al., is associated to each bar, where the possibility of bars breaking is taken into account, thus allowing to simulate the irreversible phenomena of crack initiation and propagation. In particular, the softening branch starts when a critical strain epsilon p is reached, and where the bar starts to damage. Then it continues until the ultimate strain epsilon u, at which the bar completely loses its load-bearing capacity. Moreover, to simulate the material unhomogeneity, a random field is introduced for the fracture energy by employing a variable probability distribution and by characterizing it with a linear space correlation along the three directions x, y, and z. Since the fracture energy is related to the area under the trilinear constitutive law, both the critical and the ultimate strain values are affected by the same random behavior, and consequently, the cohesive law randomly changes from one bar to another. Now the entire experimental campaign is simulated. Results from 4-point bending test are used for model calibration, whereas compression and splitting tensile ones for validation. And finally, the calibrated and validated models is used to predict the behavior under 3-point bending. Note that only the PC data are used for this simulation. By starting from the 4-point bending test, a 3D model is generated in Abacus explicit environment by using truss element. The model geometry is the same, matches the nominal specimen's dimensions, and the basic module has length 10 millimeters. The input parameters include elastic modulus, density, and tensile strength, whereas the fracture energy is estimated by using an empirical relationship based on the experimental compressive strength. The load against deflection curves for 4 random fields of the fracture energy are here plotted together with the experimental scatter band, showing a minor dependence on the random field and a very good agreement with the experimental observation. The numerical flexural strength is equal to 2.45 megapascal, corresponding to a variation of about 1% with respect to the experimental value, whereas on the right, the numerical crack paths are shown in red, together with the experimental one in black, showing a good qualitative agreement. Now the model is used to simulate both compression and splitting tensile tests by using the random field configuration number 1. And in this case, the numerical compressive strength is equal to 12.29 megapascal, corresponding to a variation of about 6% with respect to the experimental observation, whereas the numerical tensile strength is equal to 2.69 megapascal, corresponding to a variation of about 2%. Finally, the obtained model is used to simulate the 3-point bending the configuration by changing only the loading and support condition. Here, the load against deflection curve is shown, predicting a numerical flexural strength of 2.77 megapascal. Such a value is about 13% higher than that obtained from 4-point bending simulation. However, this outcome is consistent with the European recommendation, which states that such a percentage difference is commonly observed in experimental tests involving this type of loading configuration. And now let us move to the conclusions. The present work investigated the mechanical behavior of nanosilica modified pervious concrete from both experimental and numerical points of view. Adding 3% of nanosilica significantly reducing the filtration rate but leaves density and porosity essentially unchanged. The mechanical strengths are comparable to those of a plain pervious concrete, showing no beneficial effects, mainly due to workability and compaction issues, which cause a pronounced density gradient. Numerically, the simulations accurately capture the mechanical response, and also the numerical crack paths match the experimental observation. For future work, we should focus on the experimental part of the study, try to improve nanosilica dispersion and mix design. Thank you for the kind attention.